Thank you. You guys can talk afterwards, or you can leave now and talk. But I'm going to talk about the theorem and get you to think about how it all comes about. So let's start. So again, I'm just going to remind you, you don't need to know the proof. There is no need for the proof. It's always nice to just understand your mathematics, because I don't like it when it becomes magical. Okay. Now, let's just say I'm going to call the axes y and t for now, just so that it separates, so you can see when we use x, it doesn't confuse you. I'm just calling them numbers right now. Okay. So I'm going to say the y-axis is y values, and then the x-axis is t values. Right. So you've got a curve, which is this red curve here. This is your red curve, and I'm going to describe that as y equals f of t. So it's a function of t. Then what I'm going to do is I'm going to say, if we decide to find out the area, okay, if we know it's a continuous function between a to b, and I were to define the area within that interval. So let's just say I've got a point x, and I'm going to call this area, because it's a function, right? The area changes. The area between a to, 1, a to 2, a to 3, a to x, it varies. And so that means I can write a function for it because there's sort of a pattern to it. Okay? So I'm going to call it f of x. That's what I'm calling it. I'm going to call the area, it's a function, it's an area function, as f of x. If I do that, then what I can say is, if the area equals to f of x, okay, then I can say what we understand about the integral. Now there's a difference between the word integral and antiderivative. See, the integral is what we've learnt, is the whole rectangle's left and right end, and you use the Riemann sums to add them all together, and that's your definite integral, or way to find the area under a curve. Okay, and that's prior to knowing that was the antiderivative. You didn't know that. So imagine you didn't know it was the antiderivative. All you know now is, in order to find the area under a curve, you're making infinite rectangles and you're adding them all together. Okay, and that gives you the area under the curve. So that's what this is saying. This is just saying your height of the rectangle times the width of the rectangle, and you sum them all together between a to x gives you the area function. Okay? If I said that, then what I can say now is that, let's say we decide to have a bit of fun and we are gonna just derive it, okay, just by chance. We just want to know what the derivative of this area function is, hypothetically. Okay, we just want to find the derivative. Now, we know from our first principles back in chapter 9 when we talked about the derivative, if this is your area function and then I've just derived it, then remember the derivative is actually equal to the limit of, and notice I called it delta x instead of h, because h is really the change of x. Okay, if you remember, it was x moving to x plus h, and if h was really small, h is just the change. Okay, so if I just called it delta x instead of h, then we know that this is just saying your y2 minus y1 over x2 minus x1. That's your delta. Okay, so it's just your gradient. I'm using first principles. I'm just saying it is then f of x plus delta x. That's the y value that it's moved. Okay, so if you think about this is, let's say, delta x in terms of how much I've moved across. Okay, and this point here is f of x plus delta x. Okay, and this point here is f of x. Then when I say the limit of that, that's what I know, right? Then technically, remember, I defined f as the area. So when you say f of x plus delta x, you're just saying I want the area of whatever the, from where the point is to x plus delta x is. Okay, so if I'm just going to quickly define it again so you can see, I said f of x, which is this area, this is f of x, that was between a to x, and that's f of x, that's the area, right? So then what I'm saying now is that this, if we just added x plus delta x, we are now finding the area. I'm going to color it in blue, of that section. Okay? So if you think about it, if I took the blue region, which is f of x plus delta x, minus the area of f of x, that's what I'm really saying here. Because by definition before, this is f of x. So f of x goes here, that's f of x. This is f of delta x. Visually, I'm just saying, take this blue region and minus f of x, which is the red region. So if this is x and this is x plus delta x, then what you're left with is you're left with the green area, which I'm going to color here. This is what you're left with. So if you took the blue minus the red, you're left with this region. If I asked you to find the area of that region, you'd say, oh yeah, that's the integral between x to x plus delta x of f of t dt. That's what I've done here. So all I'm saying is, if I found the area between, if I found the derivative, top line, the numerator is just simply saying find the area between x to x plus delta x. That's all I'm saying. Okay, so that's your numerator. Now the key part here, which is why it's really interesting, is that I can separate this now. If I separate this, this links to what I taught you guys yesterday. You see, if I separate it, I take out delta x, it's 1 over delta x, multiplied to the area, which is the one I colored, which was between x to x plus delta x. This right here is what we knew yesterday, because delta x, another way of writing this is 1 on x2 minus x1 multiplied to x2 x delta x f of t. This is your average value. That's what we were doing yesterday. If you were to think about it visually, I'm going to draw it again so you can see. So we're saying there is this area, this is x plus delta x. Okay, that's your numerator. So I'm just going to draw it again. This is your numerator. If I re-look at it, just looking at it again, this is actually technically your average value. Average value says that between these 2 points, there exists a point, it's called C, such that the height, remember I said the average value, there's a height where you can make the rectangle and it has exactly the same area. Yeah? So that was f of c. And we knew that f of c, which is your average value, equals to this section. So all I'm trying to say right here, and this is the key step as into how we understand the fundamental theorem of calculus here. The key step here is to understand if this is the average value function, which is f of c, I can write it now, instead of writing this whole entire section, I can write that as the average value. That's your f of c. If that's your average value, now this is interesting because remember what was on the left-hand side the whole time? What was left-hand side the whole time in terms of what we were doing? We were just playing around and just said that was the derivative. And I just happened to rewrite the equation and played around with it, and it eventually came down to this nice simple description here. And the description is we're saying the limit of delta x, which is how much you change that delta x, if it approaches 0, it becomes very small, of f of c. Now what is f of c again? F of c was this coordinate right here. There was a coordinate right here. Oh, sorry, right here. And this point is f of x plus delta x. If I made delta x really small, just visually you can actually see this. So if I just draw it all again so you can see, if this point here is x plus delta x, and I made delta x really small, that means it's moving closer and closer and closer to x. That means c, some value in between c, is also getting closer and closer and closer to this point, which is f of x. Okay, now there's we can use the squeeze theorem, which can prove that point as well, that for both of them they actually come, in terms of the limits, they will come towards f of x. But at this point we can do it intuitively. That means limit of delta x approaching 0, if it does approach 0, then f of c technically becomes f of x. And so this is actually where we first started to say, oh, wait a minute. So that means the derivative of the area, okay, the derivative of the area function that you defined, you said that was the area. Okay, and how do you find the area? You found the integral. Okay, so I'm going to say the word integral. The integral is this. And so that means the derivative of the area gives you f of x. And so because of that, this is really key here, because we know that that means if I found the antiderivative on both sides, so if you think about it, if I just found the antiderivative of both sides, then this would tell me antiderivative of derivative gives me f of x equals 2, and this is the integral of f of x. So if I found the integral of both sides, integral of the derivative and the integral of f of x, this is this. And so therefore you can then say f of x, which is the area is, well, the integral of the derivative is the antiderivative. That's why you can now say, oh, the antiderivative is the integral, because the integral was just counting rectangles. You didn't know it was the antiderivative. You had no idea it was linked to derivative. Right now you've taken it, like sort of you've done it so intuitively that you're like, no, they're both the same thing. But beforehand you didn't know that. Beforehand you had no idea that you can actually just find the antiderivative. You knew how to do antiderivative, but you never knew that was actually equal to the area. So the fundamental theorem of calculus tells you that it is actually the area. Again, that's the sort of proof for it, which then leads on to, remember in my first slide about definite integrals, I said f of b minus f of a. Well, let's think about that now. So this is what we call the first theorem of fundamental theorem of calculus. This is the second part of it. The second part to it says that, okay, now if you know that the area is linked to, so we know this one definition, this was the biggest key definition at the time that really made a massive difference to sort of calculus at the time, because we now know it's the antiderivative equals the area, then, or is the integral. What you can now say, if a to x is defined by, that's the area, that means if I subbed in b, so let's choose b another point, so this is b, then f of b means the area up until b. Whereas f of x is the area for blue region, which is here. So if you then said, well, what if I took f of b minus f of x? Oops. If I got f of b minus f of x, what are you really saying? Visually, you're saying take the red area minus the blue area, and you're left with this green area. If I asked you to write an integral for this area, you would say, oh, to find that area, we're using the integral from x to b of f of t dt. That's dead. Oh no, it's not dead, it's back. And the nice thing about this is that means if we then say f of b minus f of x, which is this, take the two areas, it equals to the integral between x to b, and technically this is your definite integral. That's what I taught you at the start. I just said memorize this. I said this is the way it is, because we said at the start, we said integral of a to b of f of x dx was equal to sub b in subtract sub a. That's all it is. And the question is, well, how do you solve for f? Well, we now know that to find f you can actually just find the antiderivative, because it's the derivative equals to f of x, then the integral, you can just say antiderivative. That's why you can now say, oh, just antiderive to find f of x. To find f of x, you just need to antiderive. If you want to find b, sub b in. If you want to find the area where a is, sub a in. Because remember, f of x is the area. So when you sub b in, it just tells you area up until b. If you sub a in, it tells the area up until a, because it's an area function. Okay? And that's how it links. So you had the reason why you were able to do it so easily was because you know it was the antiderivative. That was one simple step, but this was the biggest key. That's your fundamental theorem of calculus. That leads to how to do that properly, or easier. Okay, so that was the theory. Like I said, you don't need to know this. If it didn't make sense, if you didn't understand, or if you had an inkling, you're sort of like, oh, I kind of get what he's saying, that's good. That's great. Whether you understand or not, I don't need that. And you don't need that for your exams either, and they're not going to test on that. But I just thought it makes more sense as to, some students always ask, like I described gradient derivative as being the gradient. And I was able to show you, it's just a tangent line moving around. I just wanted you to also understand why the antiderivative was the area. They didn't know. It was just up until Newton and, I always forget that guy's name. Leibniz, yeah. Those two made it, found out through different approaches in that time, and they were at the same time, so no one knows who came up with it first, but both of them figured out that the antiderivative was actually the area. But prior to that, we didn't know. Prior to that, we had to use the integral, and it was just Riemann sums at all the rectangles, and then that's how we find areas under a curve. Okay. But anyways, that's the theory. You can watch this video again just to see if you understand. Otherwise, if you like as well, Khan Academy, he describes it really well. He takes you from A to B, gives you examples on how to do it. Some of it might be challenging on some of the things he says, but if you pause and just think about what he's trying to say, it'll make more sense. So if you do want a more in-depth understanding, you can have a look at Khan Academy. He's pretty good. So Khan Academy, or you can just type in Fundamental Theorem of Calculus Proof, and he should come up as the first link. He's got a really good set of layout and how he explains it. Okay? Now, let's do some past exam questions. I got 3. I went from, again, easy to the hardest. This one, 70% of, 70-something% of students got it right, so I think it's pretty easy if you have a calculator on you, and you just find the area of the region, and then I'll give you the next one that's slightly hard, and then the last one, for you SPAS students, I expect you to all get it right. For the method students, if you get it, great. If you can really think in this sense, that's fantastic. Otherwise, we'll get there the next term. I'll go back on this extra thing I need to teach you, and that finishes off integration. Okay? But I expect all the SPAS students to get the last question right. All right, so this is the first one. Let's go. So I'm going to give you 2 minutes on a calculator. Let's go. Probably, I haven't seen her. Damn, she chose a good day. She chose a good day to be sick. After this, I envy you. Do you have to have physics? I'm asking a question. How you interpret is on you. It has nothing to. I asked you a simple question.
Hello. Hi, 12. Miss went out of his way today, but I have organised your chemistry holiday homework. So on Compass, under the Resource tab, you'll find a folder now with the documents you need to complete your holiday homework. You will need to collect a Unit 4 worksheet booklet. I've spent a bucket load of time with the printout yesterday, so please make sure you do collect it before you leave today. It's just a pile of them are sitting in Miss Leonard's pigeonhole, so make sure you collect one. If there's anyone who is not in Unit 3-4 methods, but is in Unit 3-4 Chem, so someone who's not here in this classroom but is in Chem, can you just pass on that message so that they know? I've put an announcement on Compass as well, but just make sure. Thanks, guys. Enjoy.
Thank you. Okay. Answers E. Hands up if you got the answer correct. It should be 70% of you. All right, hands up if you didn't even attempt it. All right, fair call. All right, makes sense. Your fault. Now, next one. Now, this is about 50-something%, but remember the last session to this, I talked about properties, definite integrals, and I talked about properties of definite integrals. This is easier. So the one I gave to you last time had a dilation from the y. Now it doesn't. So I expect everyone to get this one correct now. Okay? So I'm going to give you a minute and a half before you get to the last question, and that's one I expect all the special students to be able to get. Okay? So I'm going with this one. Again, if you just read the transformation, you don't need to do any calculation. You can look at that and tell me what the answer is. What'd you get?
Yeah. If you do it much later, twice.
All right, hands up. If you got your answer is A. Hands up if you got your answers B, C, D, and E. All right, good. It was either a choice between A or C. The answer is actually A. Let me show you again. You can do it either mathematically or you can do it visually. Visually, just thinking about it this way. You got a distance from 1 to 3. So 1, 3. Yeah? I don't care what the function is. It could look like that. I don't care. Okay, the point is I know the area is 5. Now read the transformation. The transformation says you're going to multiply it by a factor of 2 from the y-axis. Yeah, from the y-axis. So that means you're stretching it up or you're doubling it. So if you double it, let's say I doubled it, an extra 5. That now makes a total area of 10. Right? But then I'm shifting the graph. It says I'm shifting down. Down 3. So if it shifts down by 3, you think about down 3. This is negative 3. So negative 3. It's gone down by 3. So that's 3 units. And we know the width from 1 to 3 is 2. So this rectangle is how much you're removing because you're shifting it down. It's got, like the net area is different now. The net area you've got positive. There was 10 on the top. And now you're shifting down. So how much are you shifting down by? 3 times 2 tells the area 6. So 10, take away 6 areas because you're putting it down. It's like there's positive 10 on the top and there's minus 6 on the bottom. Then overall, you have 4 on the top and 6 on the bottom. That makes sense. That's still a total area of 10, but the net area is 4. That's why I know visually Answer's A. Alternatively, if you don't like the visual part, if that's hard for you to understand, you can do it algebraically. You can split this up into two integrals, 1 to 3 of 2f of x dx minus 1 to 3 of 3 dx. And you see it's the same thing, minus of integral of 3, which is 3x, 1 to 3. And this you can write out as, take out the constant 2. And we already know this is 5, so 5 times 2 is 10. Minus, and you sub 3 in, that gives you 9. Sub 1 in, that gives you 3. So 9 minus 3 is 6, which is what I was saying here. See, that's what you're really doing. You're just describing the transformation. So hence 10 minus 6 equals 4. So you can do it either mathematically, or you can do it visually. And I'm trying to encourage you to do it visually because it tells me that you understand it really well. Okay? Otherwise, you're just learning how to do it mathematically, which means that you just know the how, and you don't really understand the why yet. Okay? Now, last question. That was 49% that year, actually. Just under 50. Here we go, this one. Now, there are two answers that I would like that if you chose one of them, I'm still happy. I just think that there's one part I haven't taught. This is talking to the year 11s. For the year 12s, I expect you to get this correct, answer correct. Okay, it's typical in the exam to do these kind of questions. Remember I said the exams are never easy. They always do a little bit of a trick. Yeah? So I want you to have a look at this question and definitely get this one correct. So they just ask you to find the area between those two curves. You just want that little region, the shaded region. Now, which one of these solutions, I, double I, triple I, or 4, which one of these are correct? A, B, C, D, or E? Have a think.
Oh, right, yeah.
Where'd you get those questions from?
All right. Hands up. If you got the answer as A. Oh wow, really? Because that was one of the possible options that I wanted. Hands up if you got your answers B. Yep. Hands up if you got your answer as C. Answer is D. Answer is E. Okay, good. Interestingly enough, most of it should have been A or D because, well, the good thing about it is that you all understood that you had I, meaning that you knew the area, the shaded area was found by finding the total area of your rectangle, which is you've got a height of e squared times 1, so you know it was e squared minus this area here. If you minus that area there, which is area under the curve, between 0 to 1 of e2x dx, then you would have got your answer. So that's true. That's a fair call that you understood that this one is correct. The second part, or the alternative, is you didn't have to, you could actually work it out on the other way. You can work out as this rectangle, think about it horizontally, this rectangle minus the area if you're trying to face this way. Okay, so if you think about it, this is now your height of 1. So if I flip the axes and call that x and that y, okay, then you're taking these rectangle 1 e to the power 2x, but you're minusing, you're actually, or you're just finding the area of this shape here under the curve. Sorry, I'll just write that again. You can look at the axes. If that was the x, you're just finding the area under the curve of the inverse function because you're switching the x and y's. So you can switch out x e to y, and you know that that's a log function, which is that, and it will be from 1 to e2. Okay, now I haven't taught that to year 11, so that's fair call, but for the special students, you should have been able to do that. You can do it the inverse as well. Okay, so the answer was D. That's what I'm saying.
Have a good break.
Have a good break. I'll see you next term.
I have a question.
Wait, I'm just going to pause the video, otherwise you're going to be in the video.